everyone, welcome to this video on refraction. This is lesson 10 in the sound and light scheme of work. Just like in the reflection lesson, or in the video on the reflection lesson, I am not going to go through the practical here, but you should definitely do the practical. So maybe you want to demo that under the visualizer and then get students to do it themselves and measure various angles of incidence and angles of refraction using the glass block and using the ray boxes and so on. So that's really, really important. What I'm going to do in this video is just give an overview. It's kind of what might be called hinterland, but it's really important, I think, in that it comes back to our core concept that light is actually a wave, because refraction is it provides another piece of evidence that supports the wave theory of light. So I'm just going to give a quick sketch. If you've got a group who you think, actually, do you know what? For them, I just want them to know what angle of incidence, angle of refraction are and kind of do the experiment, then maybe this video is going to go, is not going to be that relevant. But certainly if you've got a group who are really want to get to grips with the science of it, they might find this sort of explanation useful. So what we can do is talk about our two old friends from the very first lesson here, Newton and Huygens. And you can remind students that the question they were asking was, well, what is light? What's light made up of? Now, after you've showed students refraction, this phenomena where as light goes from one medium to another, it appears to change direction. What we can look at is the way that Newton and Huygens both explained what was going on here. So if we draw our two boundaries here between the two media, I'll draw one for Huygens as well, like this. Remembering that Newton had the particle theory, Huygens had the wave theory, we can label here that above both lines is air and below both lines is glass, like this. So Newton, students hopefully will remember, although they might need reminding, Newton had this idea that light is made of these tiny little particles like this. So you can draw them and you can draw a little ray like this going that way. So as they approach the glass from air, you might want to add an arrow just to show that they're moving in that direction. As they approach the glass, they get closer and closer. And what Newton thought, because Newton, remember, and this is maybe, well, definitely this is going a little bit beyond year 7, but it might be helpful background for you. Newton had this theory of the universe that everything was made of these tiny little particles, and everything would be explicable in terms of forces acting between them. And the way he understood why it is that light bends towards the normal when it goes from air into glass is he said, well, okay, when they get into the glass is denser, we've got more massive particles present in there. So what's going to happen is these little particles are going to get some sort of attractive force just as they get to the glass. And what that does then is it changes the direction. It kind of pulls them down more than they would be pulled down otherwise. So then they start to change direction. And all of these particles in here have this little force which is changing the direction like this. So we can draw a few more of these. And hopefully you can see from my diagram that the light ray now appears to have bent towards the normal like this. So looks something like this. So this is how Newton explained why it is that light refracts. And what's important here is if Newton's guess is correct, at the time, late 1600s, Newton wasn't able to explain this, but he said, well, okay, if my guess is correct, then light should speed up when it goes from air into glass, because it's got this extra attractive force that's pulling it into the glass, essentially. So, something like that, light speeds up. Now, Huygens said something very different. So Huygens imagined our light wave coming in like this, our light ray coming in like this. But of course, he imagined it as if it was this invisible substance. There's this invisible substance pervading the whole universe, the ether. And he imagined that when light comes down and reaches our eyes or reaches the glass or whatever, that's kind of ripples in this invisible substance that he called the ether. So first thing we've got to do here is sketch the wavefronts. And again, we've kind of talked about wavefronts with students, but you might need to remind them what we mean by these. So if we draw some wavefronts like this, these are arriving at an angle to the boundary, just like that. Now, what Huygens suggested was that, well, okay, when this wave here, or maybe I should do another wave first. Let's do another wave here like this. One here, and maybe another one here. He said, well, when this wave arrives, this part of it is going to carry on at the same speed. But the part of it that is inside the wave is going to change direction. And the reason is because it's going to slow down. He thought, as it goes from air into glass, glass is what he described as more optically dense. So it's going to kind of change direction. And the same with this one here. And the same with this one here. So what happened is, all of these waves, they started to bunch up, but this one carried on. So this one carried on like this, as in this end of the wavefront would carry on like this. And that's why you get this perceived change in direction. So the ones that are fully inside the glass, they're all bunched up and they're looking like this, something like this. But what you can see when you then draw the ray here is that the light appears to have changed direction. One analogy I once heard about how this goes on is like if you've got a car, I think a four-wheel drive car, and two of the wheels go onto the mud, they're going to spin a bit faster and the car changes direction. It's, you know, a similar way of talking about it. And you can actually see this in water waves. So if there's kind of a sudden change in depth underneath the water waves refract. They change direction because they move at different speeds depending on the depth of the water. So you can find some nice illustrations of this online as well. So something like this. And this is really interesting as well. We can get into a whole debate here, because actually what happens here is the wavelength of light changes. The frequency, of course, is unchanged, because the frequency depends on what happened when light was emitted. But now we're going way beyond year 7, and I'm just getting carried away with the physics. But the point is here, what Huygens is predicting, and this is where you should, what you can emphasize to your students. Well, Huygens said, well, hang on, my theory, the wave theory, suggests that light slows down when it goes from air into glass. So what we have here is this lovely conundrum, this lovely question, and it's all set up to be an absolute decider, because they both give this lovely account. Both of these give a very nice explanation of how refraction happens. That's something that had been observed already. Newton said, well, my theory suggests it goes like this, but that means light speeds up. Huygens said, well, my theory suggests it goes like this, but that means light slows down. At that time, they couldn't test the speed of light in glass relative to in air. There was no way of doing that. And it was only much later, and I think, I would have to look this up, I think this came after the double slit diffraction, which kind of, that's why the double slit diffraction experiment provided the conclusive evidence for the wave theory. But when it was eventually measured, the speed of light in air versus glass, it did turn out that Newton was wrong and Huygens was correct. What actually happens is light does slow down when it goes into glass. And that's why, that's another piece of evidence supporting the wave theory. Now, that is, I hope that video was useful in terms of how to bring in some more disciplinary knowledge about the way science works. This is a great example of how scientific knowledge develops, because by deducing from our guess something that's different in both cases, and really clearly, like measurably different, speeds up or slows down, this is how we can be sure that the wave theory gives a better account than the particle theory, at least until Einstein came along and muddied the waters again. So that's really, really important, but I hope it's useful for you as teachers in terms of really understanding why it is that light changes direction as it goes from one boundary to another. And that's going to be really helpful when you're explaining why this happens to your students. I hope. Anyway, in the next lesson we will continue to look at light.